Alright, time for Smitty Werben Jensen's inequality. So the tough part of this is going to be like defining a function on the torus that does what we want it to do, but from there it's going to be nice. So let's start defining this function. This is going to take a little work, but let g naught, which is not go, be a function from 0, 1 to c, be given by g naught x equals fa plus 2b minus a x. So basically what we're doing is we're taking the values of f on the interval a to b and scrunching them into the interval from 0 to 1/2. But let's be a little bit more explicit. So g naught o, or g0, whatever, this is equal to this equals 0 equals b equals g naught 1/2. Extend this to, let's see here, to -1, 0 by gx so g naught is going to be this function on 0 to 1/2, and we're going to define g to be the function that we really want. Extend this by defining g of x equals g naught x. Okay, so let's first extend from here to here. So this is for x in 0 to 1/2, and g x equals negative g naught minus x for x in -1/2 to 0. So this is an odd extension. Then extend g to tau periodically. All of this is fine because g naught is the same on -1, or no, on 0 and 1/2, and so g is going to be 0. Well, yeah, it's 0 there. So g is going to be 0 on 1/2 times the integers, and so it's going to be like all like glued together nicely. Well, it's certainly going to be glued together. To say that's glued together nicely, we'll do that later. So actually we'll do that right now. I claim g is in C1 tau. So since f is in C1 of AB, then g naught is certainly going to be in C1 of, say, the open interval from 0 to 1/2. There. So it suffices to check that g is differentiable at x equals 0, and I wrote 1, that should be 1/2. Because if it's at 0 and 1/2, then basically you just move the result of g naught on 0 to 1/2, and you just move it around the whole, well, real line, torus, whatever. If you define it, if you work it out at 0 and 1/2, then because of our extension, it'll be fine. G naught is odd, and g naught is in C prime of tau. Did we prove that? That is not entirely obvious to me. Well, let's keep going and then see how this works. X goes to 0 from the plus. Gx over x is equal to limit as x goes to 0 from the plus g naught x over x, because they're equal. There we go. Laptop's really struggling here. Limit as x goes to 0 minus gx over x is the limit as goes to 0 minus g's 0 minus x over x minus x. Just from definition, but this is limit as x goes to 0 from the minus g naught minus x over x. Oh yeah, that g is differentiable on the g is in C1 of tau. That's kind of straightforward because f is in C1 of tau. And then if you look at what happens at the origin, the limits from both sides are going to be the same because the function is odd. And so you don't have any issues there. So, and does the same logic work? Yes, the same logic should work for differentiability at the endpoints, and so it's differentiable on tau. So yeah, that's why I didn't write it down, is because it's something that you can just kind of think about and convince yourself. And then depending on what level you're at, you can choose whether or not it's necessary to write out those details. But anyways, so this is true and this is true. So anyways, but if G naught, but the G naught we know is differentiable in tau, so these two are equal. But then we put everything together, so if these two are equal, then this thing is equal to this thing. So, but that means precisely, if these two limits are the same, that means precisely that G is differentiable at 0. One can argue likewise for differentiability at 1/2. And by one can prove this, I mean one who is not me that can prove this. Okay, so now I gotta, after I wrote my notes, I found a different way to write this that makes it a little more straightforward, because normally right here I do a preliminary calculation where you'd be like, why is he doing this calculation? But I'll put that at the end once it becomes obvious why it will be necessary. So now what can we do? Well, so G is in C1 of tau, and so I'm gonna, let's see here, continuous functions are super nice, especially on compact sets, and so in particular they're in like L1, and let's see here, this doesn't it's bounded, so it's an L2, but so because it's in a, it's really nice, you can take its Fourier transform. And so this is our new paragraph. Next, let's see here. Note that G hat of 0 equals 0 since G is odd. So that's because if you look at the integral that defines the Fourier transform of G, it's just the integral, and it's going to be an integral over an interval centered at 0, and so the evenness of it'll work out, it'll be 0. You can just write it out if you want. Or you can write it out if you don't believe me that it works. Even if you don't want to write it out, you should if you don't believe me. So now we want to look at k not equal to 0. And let me just check here. Yeah. Okay, we're going to have to scroll a bit. So, hope you remember the problem statement. I know I'll forget it. So, we have g hat of k is equal to, what is this, negative 1/2 e to the minus 2 pi I kx g of x dx. And this k is going to be an integer, it turns out, but I guess that's not really too necessary for many of these computations. So anyways, here we do integration by parts. And so we get negative 1 over 2 pi I k e to the minus 2 pi I k x gx from negative 1/2 to 1/2 plus 1 over 2 pi I k integral from negative 1/2 to 1/2. Right, plus because it's minus negative? Yeah, okay. E to the minus 2 pi I k x g prime x dx. And, well, let's see, what's this first thing? Well, remember, g is odd, and so we're going to get, it's going to cancel out, and we're going to get 0. And this e to the minus thing, this is going to give us 1, and this is going to give us 0 when you work it out. It'll be fine. It'll drop out. And so what's going to be left is the thing on the right. That's going to be this 2 pi I k times, well, if you look at what this thing is, this is just the g prime hat k. That's just the definition of the Fourier transform of g prime. Now, hence, by Parseval, we have this. G, let's just say L2 of tau squared. Here we're using Parseval. This is sum over all integers, g hat k squared. And so this is going to be equal to, well, we know that it's 0, that g hat of 0 is 0, so we can exclude that. And for the other things, when we square, we're going to get 1 over 4 pi squared k squared, and then g prime hat k squared. But now this is less than or equal to 1 over 4 pi squared the L2 tau norm of this thing squared. So now we want to compute what is this and what is this. And this is a computation I was going to do before. So let's do this. Let's see here. So here we use the substitution compute using the substitution u equals a plus 2 a minus bx, and I'll let you figure out what d mu is. Anyways, it's going to be integral over the torus of g squared with respect to the Lebesgue measure. It's going to be 2, it goes from 0 to 1/2 because of evenness. F of a plus 2b minus a x, squared dx. You do that substitution, and you get a 1 minus ba will come out, and then a to b, f, and we'll write this f of x. No, we should keep it as f of u. We'll change it to f of x later. So we get this, and then g prime squared dm. Do a similar calculation. It's going to be f prime of the same argument. Now this is going to end up being 4 times b minus a to b, f prime u squared du. Hence, let's see here. So, what's the best way to do this? Yeah, let's just see if we can fit this all on here. This less than or equal to 1 over 4 pi squared g prime L2 tau t. This implies 1 over b minus a, integral from a to b. Could probably combine a little bit of this, but I'm raising the suspense. 1 over 4 pi squared, then 4b minus a, integral from a to b, f prime x squared dx. But then what does this imply? Well, you just move around the b minus a's, in particular this one, you bring it to the other side and you get a over b fx squared dx is less than or equal to b, no, you don't need that there, I guess, b minus a over pi squared, integral from a to b of f prime g squared dx. And that's exactly the inequality that we wanted to prove. And so we have completed the proof.